Thank you everyone for coming out, and welcome to CERAWeek. So this is my second year in a row doing a talk in this pod, so hopefully this year is even better than last year's. My name is Adam Goff, and for the next 15 minutes or so, I'm going to talk to you about delivering DAC, or direct air capture, at gigaton scale. To do that, I'm going to run through 4 questions about this topic. The first one is, why gigaton scale? Why is this billion ton a year number the number the industry has settled on as our target? Number 2, who pays for it? It's going to be expensive, and where is the demand that's actually going to pay for these long-term contracts going to come from? Number 3, where will all that energy come from to supply all of these plants pulling in huge masses of air, pulling out the CO2, compressing that CO2, and regenerating the sorbent or solvent so it can be used again? And number 4, how do we scale? Right now, DAC is in its infancy. We're at thousands of tons per year, and gigatons is 1 million times that to get to that billion ton a year scale. How do we get from here to there fast enough that it actually matters and is helpful for the energy transition from here to 2050? So that is the talk. Before going into those 4 questions, I do want to give you a quick overview on 8 Rivers and on DAC. 8 Rivers invents and commercializes carbon capture technologies. We're in year 16, so we were founded back in 2008, and we have 3 main verticals. We do clean power with oxy-combustion and the alum cycle. We do clean hydrogen with something called 8RH2 that converts natural gas to clean hydrogen with near 100% CO2 capture. And we do carbon removal with the Calcite process for pulling CO2 from the air. The rendering you see in the background here, this is the rendering of a commercial plant in Alabama to pull about 100,000 tons a year of CO2 out of the air. We are in one of the mid-tier DOE DAC hubs called the CDAC hub just north of Mobile, Alabama. For those of you who are maybe not as familiar with direct air capture and what it is and how it works, I will run you through quickly a flow diagram for how we at Calcite pull CO2 from the air. We are using calcium as a sorbent, so similar active material that you might use in mortar between bricks. It is very hungry for CO2, and so we take calcium hydroxide, which is the active ingredient in mortar, and we put it in an air contactor. An air contactor really looks like a glorified strip of cooling towers, but we structure this calcium hydroxide to create a structured sorbent that can absorb that CO2 from the air and form calcium carbonate. Calcium carbonate is basically limestone. So this is something that we have familiarity of dealing with at billion ton per year scale. That limestone has CO2 from the air. We have to heat it up to pull that CO2 off so we can store it underground. We do that in an oxy-fired kiln. So we're heating it up to about 1,000 degrees Celsius. This is the regeneration phase where we're pulling CO2 off and storing it underground, and we're regenerating that sorbent. So as we get into the energy questions later in the presentation, most of the energy is coming in that regeneration phase for the kiln, and also some for pulling that air across the sorbent. This is how we at Calcite do it. There are a couple different approaches, but they typically have an adsorption phase to pull the CO2 and a desorption phase to release that CO2 for storage. Starting with question 1, why did we end up at gigaton scale? ChatGPT helped a little bit here with these 3 images that we're going to walk through, as you may notice. Starting with 2.5%. 1 billion tons is just 2.5% of global emissions. It's a small lever. DAC is not the majority solution to climate change and decarbonization, nor should it be, because it is one of, if not the most expensive approach we have for reducing emissions. DAC is a small wedge, but it's useful because there are some industries that are too hard to abate, whether it's something like agriculture or something like airplanes, where they either don't have any other options, or those options are somehow even more expensive than emitting CO2, letting it disperse in the upper atmosphere, and then pulling it out after it's already diffused. So that is the part of the decarbonization challenge that DAC is addressing. 1 billion tons is maybe not as much as it seems. But for specific industries like aviation, it is. 1 billion tons is also about 100% of the annual emissions from aviation. So when we think about getting DAC to 1 billion ton a year scale, we're probably pulling together 3 or 4 hard to abate industries, a portion of the aviation solution, a portion of the emissions from, say, peaker power plants that only run 10 or 20% of the year, a portion of the emissions from agriculture that we don't have any other way to abate. Those are the emissions we can add up to get to this billion ton a year, 2 billion ton a year scale that we think DAC is a compelling solution for. Now, I did ask ChatGPT how much this was going to cost, and it gave me the not very helpful answer as $0.00 billion per year. But it's actually not as far off as you might think. One, because we don't know. DAC is too early to have high confidence in your cost predictions. But to do billions of tons a billion tons a year is going to be in the order of magnitude of hundreds of billions of dollars a year. So it is a large number, which brings us to our third question. Who's going to pay for it? We care about this question a lot, one, because we're currently working on our first commercial DAC plant, and we have to go out and sell these offtakes. We have to go talk to and find long-term offtakes for direct air capture. And because long-term, in our view, the who's going to pay for it question is what's going to drive the speed of DAC and the scale of DAC. If there's not enough customers, we're just not going to be able to build that many DAC plants. Right now, for plants that we're seeing, it's a combination of tax policy and voluntary markets. So what voluntary markets at this point means is really, for us, three main industries: big tech, big airlines, and big banks, who have an interest in cutting their emissions, even though they don't have to. That's the voluntary and voluntary market. No one is making them, but they've made commitments themselves to their stakeholders that they're going to reach certain emissions targets and often net zero. And these are some of the biggest companies in the world. They can actually afford DAC as part of their portfolio as they look for the highest quality approaches to remove or offset the emissions they have no other way to reduce. And we combine that with tax policy. So as often happens with new technologies, the government helps pay part of the bill to get it off the ground. This is how we built the solar industry. This is how we built the wind industry. For carbon capture, the Inflation Reduction Act created a large tax incentive for direct air capture that we can use to make those offtakes, which are quite expensive, cheap enough that we can sell them into the voluntary markets and have the private sector foot the rest of the bill. A key thing with tax policy is even though the government is subsidizing you, they're not taking your credits, right? So that they're giving you some number of dollars per ton for your DAC, but they are not claiming that emissions reduction. So you can stack the tax policy, whether it's Canada's investment tax credit or tax policy in the US, with the voluntary markets. That is the near-term answer to who pays for DAC. It's not the long-term answer. If we're going to get to billions of dollars a year in offsets, you're not going to see that in the voluntary market. No corporate board is going to keep approving hundreds of millions of dollars a year in expenses they don't have to do. That's where we get into compliance markets. Compliance markets look a lot like cap and trade, where the government sets some emission reduction target the industry has to hit. And so then there's some kind of trading scheme where they purchase reductions, and for everything they can't remove or reduce, DAC becomes a viable option. The good news is we already have compliance markets. You have the low carbon fuel standards in Canada, California, New Mexico, Washington, that are cap and trade markets covering transportation. And you have something like Corsia, which is a similar concept for airlines. Or you have, say, the EU emissions trading system. The good news is these compliance markets exist, and they actually already have a fairly large scale, so they're covering hundreds of millions of tons of CO2. So these are not small trial markets, and the prices are sometimes quite high. You'll see prices up to $200 per ton in California. The EU emissions trading system with the Ukraine-Russia crisis was going over $100 a ton. That sounds great. The problem is the compliance markets are not yet financeable. If we're going to build a DAC plant, we're going to start building it today. It's going to come online in 5 years and run for another 15. It doesn't really matter to me what the price is today. I don't get the price today. I need to have price certainty from 2028 through 2040. And this is the real challenge we see for compliance markets, is how do we design compliance markets that support building this long-term infrastructure and giving us enough price certainty to finance it. Something that maybe looks more like a contract for differences model. The current compliance markets work really well for power systems, where you're switching coal plants for gas plants or gas plants for renewables. They're not as well suited for building this long-term infrastructure that needs 10 to 15-year payoffs. So if we do manage to solve the who pays for DAC question, the next question is where will the energy come from? The chart that's here comes from the UK's Climate Change Committee that did this great study where they looked at if you had 1 megawatt hour of clean power, how could you get the most CO2 reduction bang for your buck? At the far left here, the best option is displacing coal generation. As should surprise no one, is how you get the most CO2 reduction from clean power. After that, powering an EV. Third on the list, heat pumps, then displacing gas generation. DAC comes in fifth at that yellow bar down there, just beating out making methane from green hydrogen or making synthetic jet fuel. DAC is not the best use of clean electricity, and where we are right now, clean electricity is going to be supply limited for quite a while, quite a ways to come. What does that mean for scaling DAC? I think we have to be very conscious and cautious about additionality, and making sure we're not taking clean electrons that were really going to go to displace a coal plant and pulling them into direct air capture, inadvertently causing emissions increases instead of emissions decreases. I think there's two good ways to go about this. The thing we're doing at Calcite is we're not really going to use electricity. So one way around this is don't build your DAC plant to use clean electricity if you don't have enough clean electricity to use. So we're able to use thermal fuels like, say, natural gas instead of electricity. We don't have an additionality concern with natural gas from an emissions perspective. The thing we have to then do is we have to capture all that CO2. We have to capture CO2 from the natural gas input alongside the CO2 from the direct air capture for that to work. If you are going to do an electricity-heavy DAC system, we think you're going to have to use electrons that weren't able to displace a coal plant or power an EV, stranded electrons. That might be solar and wind plants that are too variable to feed into the grid or too remote. That might be Canadian hydro. The nice thing with DAC is you don't have to be near population centers. It's not like a power plant where you want to be near the use for the power. DAC is pulling CO2 from the atmosphere. The atmosphere is all around us. So you can locate DAC plants in places like southern Chile or northern Canada where there is an excess of clean electrons that couldn't otherwise be used for higher and better uses. So going on to the fourth question here is we solve all of those things, how do we actually scale? We're at 1,000 ton a year, kiloton a year industry. How do we get to this larger scale? The first problem we have to solve is pilot to first of a kind. That's where pretty much the whole industry is right now, is you have a pilot plant and we're building that first plant scale. And there's two questions inside of that I want to talk about here. The first one may seem a bit obvious, but for direct air capture, the air really matters. It's really important that when you're testing out your system, the quality of the air, the temperature, the wind speed, how much pollen is in it in the spring, the humidity, that all really affects your performance, much more so than with a refinery or a power plant that isn't so dependent on moving unimaginably large volumes of air. So we think it's important to be able to simulate those conditions in your pilot plant that are similar to your large-scale plant. One other example of this is CO2 is well mixed in the atmosphere. I know we're all familiar with 420 ppm and these kind of ppm numbers. It's not all that well mixed at ground level. So when you start building plants and you put CO2 monitors on your site, you're going to have evenings where it spikes to 600 or 700 ppm because the trees in the forest are respirating at night, which is what we've seen at our site. That's good news for DAC, right? Having more CO2 in the air actually makes it cheaper. Or you might be building in a cornfield in the Midwest and realize that during growing season, the CO2 dips down to 200 ppm. So it is very important to test in the actual air. The second thing we think is that for these first couple plants, it's really all about CapEx. As important as energy is going to be for scaling, when you're looking at these first plants that are hundreds of dollars per ton, energy is a fraction of your cost. For the first couple plants, you haven't come down the cost curve. These are really expensive, and so anything you can do to get your capital costs down faster and to use cheaper components, that's is what's going to make it affordable for you to actually build the first couple plants, to be lucky enough to be at a point where energy is actually your binding constraint. The last point I want to make here, as we think about CapEx, one of the solutions people propose, which I think is the right approach, is modularity. We've seen all these amazing cost declines with solar and batteries because they have this repeatable module that they can rinse and repeat and print out and get down the cost curve. We do need to see a similar approach with DAC. We're going to need to see repeatable plants where the supply chain can build the same thing over and over again. That's part of the solution of how we're going to get to costs that society is actually able and willing to pay. But I don't think it's going to be exactly the same. If you're in solar, right now, you can go build a solar factory and you can know that you're going to have demand for those solar panels for the next 15 years, so you can finance your factory. I think building factories that supply DAC plants is going to be hard because the demand is just much more uncertain. It's not electricity where there's hundreds of gigawatts of demand. Building a DAC plant that is then going to supply DAC factories or DAC plants you don't know are going to exist is going to be very difficult. So as much as possible, we want to repurpose existing supply chains. So you want to have components for DAC plants that can be modularized, but aren't entirely new widgets that you have to build new factories for. That's just going to add on to the CapEx budget that's going to make it very difficult to scale. So thanks for your attention so far. This is a snapshot of how we're thinking about DAC at 8 Rivers. We'd be happy to take additional questions from the crowd. Please feel free to reach out to me by email, or you can come by and see the 8 Rivers booth. We're about a block down that way in the Hydrogen Hub. So thank you so much.
Thank you, Adam. We have some time for some questions.
You said you were here last year. What's changed over the past year for you?
I think last time I was here at CERAWeek, it was We were in the process of writing our DAC application, so we were all at the stage of thinking about our initial commercial plans, or we at Calcite at least. I do not think we were as serious about financing them, so I do not think we, 8 Rivers, or the industry as a whole was as far along to actually be thinking about the permitting approach, the EPC contracting strategy, actually getting 10 to 12-year offtakes for DAC, actually getting tax credit deals that go along with it. I would say one of the things I'm excited about, concerned about, is making the tax credits financeable as well. So a lot of the revenue is coming from 45Q. You're going to need to have certainty that those tax credits are you're going to get 80 or 90 cents on the dollar for them in 2035, 2036, 2037. So I think the industry as a whole has gotten a lot more focused on those long tail questions that matter now, so you can actually get bank debt or actually get project finance equity.
Additional questions?
You're talking about using natural gas to power the DAC plants. You're going to have to get to really high levels of carbon capture on the post-combustion carbon capture of the flue gas stream, right, for the methane. Because if you've got just a small amount of methane that's emitted from that plant, then that's going to offset the carbon that you're capturing from the atmosphere. Like, what sort of capture rates do you need to get up to?
So I'm going to answer that in 2 ways. It's a great question. If you're using natural gas as your thermal fuel, if you're capturing CO2 from the atmosphere and then emitting it somewhere else in your process, that doesn't really make any sense, right? You have to be capturing north of 97, 98% of your CO2, and you're going to, because you're getting paid to. If you're getting contracts for hundreds of dollars per ton of CO2, it pays to capture those higher rates. Our approach is using oxy-combustion, so I think it's often hard to get to higher rates when you're using amines, which kind of tap out at 90 to 95% capture. When you're doing oxy-combustion, you're burning impure oxygen, you don't have any nitrogen in there. It's easier to get to those really high rates. The other part of that question is methane. Is if you're using natural gas as a supply source, if you have high methane leaks, you're kind of running in circles here. So you're going to have to source the highest quality natural gas that has, less than 0.5 or less than 0.2% methane leakage. Your customers are also going to make you, if you're going to sell DAC to a big tech company, they're not going to buy it if they don't know where the gas is coming from and know the methane leakage. I think the other thing in the near term is there are other sources of methane that aren't, oil and gas. You can use renewable natural gas. That's useful for the first couple plants. If we get to gigaton scale, it's going to be fossil-derived natural gas. But in the near term, you have some of these landfill gas or dairy manure gas that you can use to blend in as well.
So how do you scale up the transport and storage side of the CO2 if you go from smaller scale to larger scale?
This is a great question. Not my personal area of expertise, but I'll give it a shot. How do you scale up the transport and storage infrastructure? I think one of the nice things with transport and storage, or it's good and bad, it's harder at smaller scales. It's unlike DAC, where DAC is easier at smaller scales. It's much easier to build a big pipeline. It's much easier to have a large CO2 storage hub. It's pretty hard to only do 1 million tons. The numbers work much more poorly if you don't have enough customers going through. So the way to do it is you have to aggregate enough demand. You have to be, right now, you have to be somewhere where there's enough sources of CO2 for multiple projects so you don't have single project risk, so you can finance a pipeline and finance Class 6 wells. I think something that helps direct air capture is we can locate where the storage is, right? It's not like a power plant where we're constrained by the electric grid as much. We have more degrees of freedom in locating these plants, but I think aggregating demand, if I was developing transport and storage solutions, I'd be really nervous if I was dependent on 1 or 2 plants, because any permit, any delay in a transformer can delay that project and delay your returns on the transport and storage side. But I will say something else I'm more hopeful on is the Class 6 process is going pretty well. I think that's the thing a lot of us have been worried about for a number of years, but we are seeing a lot of Class 6 applications go in, and the ones that go in with fairly complete are moving through at a reasonable pace, where I think now we're all more worried about transformers, which we weren't talking about 12 months ago, than we are about the EPA's time to process Class 6 permits.
Additional questions?
What sort of costs do you think you can get down to per ton of CO2 captured?
The industry says it's aiming for $100 per ton. If that hundreds of dollars per ton is in like 2022 dollars, that's maybe achievable. I don't think in 2028, with inflation, you're going to be hitting $100 a ton. I think it's a good cost target for the industry, and I think you'll keep seeing $100 per ton as a target. But to get there, I think you're getting as close to that as you can. I think sub 200, yes. I think you approach 100. Unless you're going to assume like the energy is free, or I'm getting state-sponsored debt with like a 2% interest rate, like you can get there, but it requires some heroic assumptions. I think that between 100 and 200 is the more realistic midterm target.
So in terms of the pilot plant that you talked about, can you tell us where you are on the timeline and what the timeline is?
Sure. So Calcite, we're building a pilot plant that's going to be online in about the next year. So we are actually doing a phased approach where we have multiple parts of it coming online, and that'll be coming online over the next year, which will support us having a full-scale commercial plant coming online in the next 5 years. So you have to have the pilot plant to complete feed, to then have a 24 to 30-month construction period. So we're at work on the pilot now down in Alabama at that same location where we're looking to scale up a commercial plant.
Some additional questions? Those in the back?
I was struck by the fact that you're producing calcium carbonate from the process, which is, of course, where concrete or cement is made. And I've been trying to think, as you've been talking, are there any synergies between what you're trying to do and what is already the biggest production process, one of the biggest production processes in the world? Any way you can, to address the challenges that your industry faces by working with that? I couldn't come up with anything sitting here, but I thought I'd toss it to you.
So at small scale, yes. So in a process like this, you're going to have purge, right? You're going to have not all of the calcium carbonate is going to cycle back into the kiln, and so some of that purge is actually a useful input as aggregate or into other processes that need GCC, ground calcium carbonate. As you get to large scales, it doesn't work at all. Like calcium carbonate is so widely used because it's dirt cheap. Like it's like $7 per ton, which if you think about how much material that is, like it's just the cost to get it out of the ground. You're not ever going to move it very far. So at small scales, yes, you might be able to feed into a local market that's undersupplied with GCC, but as you scale up, you're not going to move this stuff more than 50 miles. The cement industry has lots of plants all over the place to solve this issue. So I don't think it's going to be a long-term driver of DAC. I think other building materials like CO2 into carbon fibers or carbon nanotubes, but I don't think the rocks themselves are going to be a game changer.
Anybody else?
Great. Well, thanks everyone so much. Feel free to come up to me afterwards, and hope to see you guys at the 8 Rivers booth later in the conference.